Welcome to Think Science. I'm Nathan Cohn with Texas Public Radio. At each of these talks, our goal is to bring you in and out in an hour, having learned a little more about the subject at hand. And our focus today is on the future of artificial intelligence and the challenges that come with its development and use. Today's presentation is made possible by CodeUp, Mind Science, and UTSA Knowledge Enterprise, and by you as a supporter of Texas Public Radio. We have three great presenters who will offer an overview of their research today, and I know what they have to say will spur some great questions. You're going to have an opportunity to ask some questions today during the hour as well. When it comes time for the Q&A portion of the panel, if you would type your questions in the chat room, and I'll relay them to the panelists. That would work best. 4 years ago, Elon Musk, love him or hate him, stood in front of a room full of state governors and said, artificial intelligence posed an existential threat to human civilization. Was he just blowing smoke? Well, knowing Elon Musk, it could have been either figuratively or literally. Sam Altman, founder of the nonprofit OpenAI, just recently said AI will be a revolution just like the agricultural revolution or the industrial revolution or the technological revolution earlier. But really, artificial intelligence is brilliant, and it can be a little bit concerning to us. Everything from your Netflix recommendations to police arrest warrants are affected by computers running AI programs. But who's feeding them the data? And what are companies doing with that data once it's in the system? And will computers ever truly be able to think like humans? Well, we have some great presenters today who are going to address some of these issues and more. Let's start with our first presenter today, Dirisha Kudithipudi, director of the Matrix AI Consortium at UTSA. Her areas of research interest include neuromorphic AI systems and architectures, AI algorithms, and energy-efficient machine learning. Okay, let's welcome to you, Dirisha. We're looking forward to hearing you.
Thank you, Nathan, for that kind introduction. Are you able to see my screen?
Yes.
Good afternoon, and thank you, Texas Public Radio, for initiating this very important discussion. Today, the total spending of AI systems is expected to reach about $97.9 billion by 2023, and that is about from $37.5 billion in 2019. And as Nathan pointed out, AI systems have been disrupting several technologies. Today, they can compose text, audio, and images to a very high standard that humans have a hard time telling the difference between synthetic and non-synthetic outputs in certain technologies. And scientists are using AI models to learn representations of chemical molecules for more effective chemical synthesis planning. And AI is disrupting several other technology domains. Yet, today's AI has significant limitations in terms of generalizing, in terms of robustness, in terms of transparency, and also in terms of the amount of energy it consumes. Achieving the full potential for AI technologies poses challenges that really require a radical transformation in the research approaches and also how we are bringing research teams together. So we argue that taking inspiration from biological brains can play a very vital role in solving some of these problems as we are building the next generation AI. So before I go into what some of the exciting research our team is doing, I wanted to share these amazing group of student researchers, both from undergraduate and graduate programs, who are helping shape this next generation of AI systems. So let us see what is so interesting about the brain. It is well endowed with 100 billion neurons, which would, with 200 neuron firings per second and 1,000 connections, it would translate to about 20 quadrillion calculations per second. And amazingly, brain is able to do this all with only 20 watts of power dissipation. And if we compare the world's most fastest supercomputer today from Japan, which is the Fujitsu Fugaku, it has about 415,530 teraflops per second operations, but the power consumption of that is 20 to 30 megawatts. So some can argue these are solving two different types of problems. And yes, indeed, the brains are solving very different types of problems compared to our modern day supercomputers. But still, it's astounding to the amount of power dissipation these supercomputers are consuming versus the task that the brains can do, and the power consumption is only 20 watts. And more importantly, brains are working exemplar models, as in they can process information with very minimal resources. They can work with unstructured data, which we often call dark data. It's an example of a very complex system where functionality emerges as a global property. And it is plastic at all levels. It is not hardwired like systems that you see in modern day computing. And it is not only plastic at all levels, but it is able to learn continuously through its lifetime. And the learning itself is very robust, and it is learning from unreliable primitives such as the neurons and the synapses. And it is perhaps looking at this brain as a source of inspiration can help us or offer us insights that we would otherwise miss in building these AI systems. So a key takeaway I want you to take from this slide is that our research group is looking at brain as a source of inspiration to building these AI systems to solve some of the current challenges we have, but we are not trying to mimic the brain because we are still trying to understand this. And there are several real-world interactive applications where intelligence is required on demand, and it is required on research-constrained platforms like the ones you see here, where brain-inspired AI systems can flourish. If you look at the dynamic learning capabilities, such as the video tracking example that you see here on the left, an app that was developed by my students in the lab, or the smartwatch health monitoring, or the smart routing in augmented reality or prosthetics, there is a lot of opportunity for deploying brain-inspired AI systems. And for example, in applications like this video activity recognition or video tracking, this is a rapidly growing one where 80% of the new digital data is going to be video. So there is going to be a significant impact with these type of technologies. So as I mentioned earlier, current generation AI systems have several limitations, and I want to show a couple of examples here. On the left, again, these are toy examples. On the left, you see the video of a car trying to park and merge and pass in traffic. So just a second, sorry. So in this example, what's happening is that the car is initially the AI system was trained to park the car, and it's able to do that with high efficiency. And in the second example, it was trying to also learn how to merge into the traffic. So it is able to do that task well, but what's happening is it is not able to park efficiently. So the performance has degraded in the first task. So what's happening here is that as we are introducing more and more new tasks into the AI system or model, once it's deployed, it is not able to perform well or generalize well. And if you look at the example on the right, just a second. If you look at the example on the right, this is a case where what happens when you have unpredictable inputs or scenarios that you face in real world situations. Is the AI agent able to learn quickly and use knowledge across tasks that is, it has learned from previous examples. You can see that it wasn't able to do well when a new task was introduced. It wasn't able to adapt quickly. But if we look at the biological brains, they're amazing at doing these tasks. So here are some, in this cartoon here, we show some of the insights or features that these AI systems can have in order to solve some of the problems I mentioned in the previous slide. It should be able to learn with very few examples. It should have autonomous nature. It should be able to learn dynamically in an online fashion. And there are a lot of examples where you probably do not have the luxury of having large data samples. You example in space or in kind of emerging diseases. So you would want to be able to work in these scenarios with AI models that are able to give some kind of predictive analytics or some kind of classification, because collecting data could be an expensive and time-consuming process. So, and also importantly, efficiency. Can these AI systems do this with very minimal energy consumption? So what I'll do is provide some examples that our lab is working on in order to solve these problems. And these are primarily brain-inspired models. So the first model that I'm showing here is inspired by the neocortex, which is considered the powerhouse of intelligence, and it is responsible for higher cognitive functions such as perception, language, and decision making. So the left side shows the biological inspiration, and you can see that it has several layers, or we call this hierarchy, and it has redundancy in the number of neurons, and it also has sparse distributed representation. So we use this model to build this AI algorithm that you see on the right, which is called the hierarchical temporal memory. And this model is able to work with limited data. It is able to work in an online fashion and is able to detect anomalies in streaming data very efficiently with extremely low energy dissipation. And some of this specific effort is sponsored by Seagate. And if we look at the next example, here we are looking at the cerebellum as a source of inspiration, so we can process the input streams rapidly. Again, the left shows the biological inspiration and the right side shows the actual AI model. So in this model, what we were able to show was that when you look at traditional AI models, they take about 4 to 5 hours of training on complex data, whereas we were able to perform that in a matter of minutes in this case. Another model that is inspired by the plasticity we see in the brain called neuromodulation. And this specific model is very advantageous when we want to deploy them on the sensors, on the IoT, or the edge, because this model is able to work with very few data samples and also is very compact and able to consume very little energy. Here's another example where we are looking at plasticity as a source of inspiration in the brain. And here we are particularly exploiting something called neurogenesis that implies generating new neurons or synapses throughout our lifetime. That's what is shown on the cartoon on the left. And these new neurons and synapses enable us to learn rapidly new information throughout our lifetime. And that is what we try to emulate in this AI algorithm, which was able to learn continuously as new data is being presented to the system. So we do have fun with some simulation environments where we kind of use this models that we have built. So you can see on the top here is a scenario where an agent is deployed to kind of see how it navigates through a wildfire in a forest. And it's not able to do well. But once we train it with our AI model, it is able to navigate through all the hurdles and unexpected inputs that get into the system and do the specific task, in this case, perhaps rescuing someone who is caught there. Another example here is how a robot is exploring unknown scenarios and before training, which is shown on the left, and it is kidding because the specific environment is new to this. And whereas if we see the one on the right, you could see that it is able to navigate and reach to the proper destination in spite of the hurdles it presented. So this is how it performs when it is trained. So there are several other exciting projects that we do in our lab, but one of the main theme is to kind of look at brain as a source of inspiration and look at energy efficient AI models. So the key takeaways I would say from this specific approach is that brains provide a very rich source of inspiration as we are developing new types of AI algorithms and systems. And these models can be complementary to the traditional approaches to AI, where we use logical and mathematical based models. Though we do have those models in this brain-inspired systems, these would be more complementary in nature. And energy efficiency is a hallmark feature of these systems. And in the future, we are going to see brain-inspired and bioplausible models play a significant role in AI systems. And finally, I want to make a point as the nature of this field is cross-disciplinary, and solving the grand challenges in the field requires scientists from multiple disciplines to work together. We have recently established Matrix and AI Consortium for Human Wellbeing at the University of Texas, San Antonio. And our goal here is to conduct transformative research in the design, use, and deployment of AI that enhances human life. So if you're more interested about our consortium, feel free to go to ai.utsa.edu. Thank you very much for your time.
Thank you, Darisha. We appreciate that. And we'll be back with some more questions for you as we move towards the end of the panel today. That's really interesting and thought-provoking research that you're working on there. I'd like to bring in Michael Hartnett, who's a research computer scientist at Southwest Research Institute, and he has a background in machine learning, data management, and informatics. His primary focus is applying data-driven modeling to assist experts in emerging domains. Michael, thanks so much for your time today and for being here.
Thanks for the introduction and the opportunity, Nathan. So I'm Michael Hartnett. I work at Southwest Research Institute, and I'm hoping today to present some examples of how SWRI, Southwest Research, is currently applying machine learning in the 21st century. So I'm going to start at a broad organizational level and then drill down into some of the projects that I'm personally involved with. A little bit about Southwest Research. We are a nonprofit R&D organization with about 3,000 employees on a large campus here in San Antonio, Texas. Our main focus is on conducting applied research, which means taking those cutting edge concepts developed by people like Darisha in academia and adapting them into solutions for specific problems faced by industry. We serve both government and commercial clients. So SWRI consists of 9 technical divisions over a broad array of fields. I'm going to focus today on intelligent systems because that's where I work, but you will see in the following examples of AI application sort of the power of collaboration and how that enables us to provide innovative solutions. So the first field I'll discuss is automated vehicles, which is, Southwest Research is a pioneer in this field, developing machine learning technologies that enable the future of autonomous vehicles. So on the first top left example, my computer's kind of freezing a little bit, but in the top left example, you can see real-time object detection and tracking in a moving vehicle. Can everyone see, is the screen moving at all? No?
The motion is not happening on the
Okay.
screen right now, but it might work itself out with the next slide if you want to just describe what was going on in the animation.
So there's object detection on a moving vehicle. Both, I guess I should say, detection of vehicles and people. So classifying what the objects are in the image or in the video. In the top right, there's an example of anomaly detection, where we have mapped out the nominal traffic patterns at an intersection in order to detect wrong way drivers. And then on the bottom half of the slide are the right side is an example of a patented technology at Southwest Research, markerless motion capture, where we use machine learning instead of the sort of CGI suit that you might be used to seeing to capture the motion of a human. And that technology is then extended with our motion prediction system, where we predict where a pedestrian will be over a given time horizon, which can be the difference between an autonomous vehicle responding in time to avoid or avoid hitting that pedestrian. I can't move to the next slide though. I think I've lost.
If you have to go out of the presentation mode and just go to the slide itself if you need to.
Yeah, it won't even let me end the slideshow. And sorry for the technical difficulties.
It's the world we're in right now.
Yeah, I've lost my mouse as well. So,
do you want me to? Shall I bring up Mutale for a moment and then we can come back? Okay,
yeah,
great. Let's do that. No problem. We're going to roll with it here. Mutale Nkonde is the founder of the nonprofit AI for the People. And what you've heard from Dirisha and also Michael, which you'll hear from in just a little bit as well, are some of the tech and practical ways that AI is being used in the field. AI for the People's mission is to produce content that empowers general audiences to combat racial bias in tech. Mutale holds fellowships at the Digital Civil Society Lab at Stanford University and the Institute of Advanced Study at Notre Dame, as well as being a key constituent at the 3C UN Roundtable for AI and an affiliate at the Berkman Klein Center for Internet and Society at Harvard. Mutale, thank you so much for your time today, and I'm really looking forward to hearing about your work.
Yeah, sure. And thank you for inviting me, everybody. Hey, Texas. I'm here in New York, and we've definitely been thinking about you over the last few weeks and wish that we could have been with you earlier. So just in terms of the information that my colleagues have shared, AI for the People is a communications firm. I do have a background in journalism, and during that time, over the last 20 years, have really told stories that translate how the amazing research being done in both places, university as well as research institutes, as we've seen, translates into everyday life. So AI for the People, we're really interested in predictive algorithmic systems and what they look like within the AI context. And you've heard previously some mention of predictive analytics, but just to give everybody some background so that we're all coming from the same place, many of the systems that we use that help us mimic brain activity, so systems that speak to us, systems that we use to write, systems that recognize us, are programmed to have the ability to anticipate what we'd want next. So the easiest example of that is if you have an email address, I'm going to pick Gmail just for fun. Often when you're typing, You might start an email with a name in the subject line and it says dear, and then it autofills the name. So that's really coming from an AI system that has been trained. The way that that particular system has been trained is that it has been fed billions of emails that we're sending across the Gmail server every day. And it's found a pattern that usually when you have an email address and you type dear using English, using the English language, the name in the email will correspond to who it's being sent to. So that type of connection is low risk. If they get the name wrong, it doesn't really matter. But the questions I ask and the questions that I've asked over the last 10 years while working in technology, both within industry, my very first job was working opposite Google's external affairs department and looking at some of the nonprofit work that they were doing, through to my research work and through to my communications work, asks what happens when these systems are making high risk decisions. So to just let you know the type of work that I'm looking at and how kind of AI intersects with race, I'm going to give you two broad areas that we work in. We work in information integrity, because we're really interested in how those algorithms that predict what we want to see in social media impact not just what we see, but how trustworthy that information is, and then how disinformation or misinformation leads to real world outcomes, as we've seen January 6th very recently at the Capitol, or even more so, even more recently, if we think about the impact that rhetoric is having on our Asian American siblings. So I definitely want to, offer solidarity and send my love out to folks in the Asian American community. So that's one area of work. The other area is biometrics. So in the technologies that we've had described, none of them have really looked at how in the next $1 trillion isn't going to be made at our screens. It's actually going to be made through ambient technologies. So technologies that open doors when you get there because the door knows that you're supposed to be there. There's some type of recognition. Many people, not me, because I'm paranoid about security, speak to voice-activated devices. So I would never ask Siri to turn anything on for me or buy me anything. That would seem ridiculous for me. Millions of people are. And in both those technical classes, there is a pattern of Black people, poor people, women, non-English speakers, and folks from the global South to be disadvantaged. And I'm in a very unique position where not only am I racialized as Black, but I'm feminized, I identify as a woman, and I'm from Zambia, I'm from the global South. So there's a couple of different places where some of those disadvantages intersect in my own life. So just to go to the disinformation work, I had described prior how these technologies are given large data sets, which are called training data, to learn how to perform their task. So in the first presentation, we saw a robot that was falling over because it didn't know the environment. Then we saw a robot that was just walking around. The difference between the two robots was the robot that was walking around had been shown that environment, shown the pitfalls, and because it is a learning technology, it's mapping the brain to develop the intelligence of, if you think about it in the context of walking, sight, muscle coordination, and then anticipating what's coming next to walk. The same thing happens on social media. The way that those algorithms are trained, though, is that they monitor your behavior. They look at what you like, what you click, what you share, what you comment, and then they feed more of that same content. The thing that's driving that constant feeding loop is the ability for the social media platform to monetize. So I'm not a Facebook user anymore, but when I was a Facebook user, I would find messages about racial justice, about plants, cats, things that I was engaging with would be fed with me, but so would corresponding advertisements. And there is another element with the way cookies work to follow you around the internet, see what you like, and feed those back to your feeds as well, which is somewhat of a different, I was going to say Zoom, but this might be a different platform. But you get the idea. You go online and then all of a sudden there's some Uggs. You go online, all of a sudden there's Perrier water or McDonald's or whatever you were seemingly thinking of. The problem that we found, though, in our work at AI for the People is the messages that sometimes people of color, particularly Black people, are fed are based on racial stereotypes that position us in a negative way. So LaTanya Sweeney was did a really strong case study around this, where she found that when she typed her name into Google search, LaTanya Sweeney, which is a name that is racialized as Black in America, ads for bail bonds were coming up next to her name, despite the fact that she had no criminal record. The only thing that happened is that proxies within the training data, so not race specifically, but maybe it could have been the number of times that the name LaTanya was connected to people that lived in a certain zip code. And we know that zip code becomes racialized because of redlining. And so because of redlining, neighborhoods, zip codes themselves became coded as Black and white, rich and poor. And when that is combined with things like name, you get that racial bias. The same thing happens on social media. So you would see, we see this in the context of elections, that when we built a data set in 2020 that was looking at racially targeted disinformation, and we found that Black folks were being targeted by a particular disinformation network. And the way that it worked was it would use seemingly breaking news events. So things like Kamala Harris being announced as president, and it would say something like, you know, Kamala Harris has been announced as a presidential candidate. She's not really Black. And we were like, well, you know, she kind of is, and don't vote for her. And that what was really interesting to us was the way that this breaking news event was fed to Black people's feeds, because we probably had liked Obama, we probably had liked these other political figures of color, but in it being fed to us was this harmful information. And we characterized it as disinformation because it was false information with the desire to manipulate. So that's a really applied example of how AI systems that drive social media algorithms, which are nothing to do with elections or any one event, are, once they become part of our social life, are having this racialized negative impact. The other type of work that we do around biometrics has been really looking at the use of biometric technologies by government agencies. So that could be the police, that could be social services, that could be housing. And two really quick case studies around that. So in the context of policing, we're now beginning to see case studies where facial recognition, which is a technology that says it's going to see. So people are always asking me, what is AI? And I always say, if you think about a machine that can perform one of the 5 senses, sight, smell, taste, touch, hear, if a machine can do that, then that makes it artificially intelligent, right? So that's a really simple way of thinking about it. In the case of facial recognition, the promise, the technical promise, is that this machine can see your face and then you can do whatever you want with that identification. The way that it's being used is within the security industry. So this can be government policing, or it could be anything as simple as a Ring doorbell. So you could have a doorbell that's constantly taking pictures of people outside. But what you don't know as the Ring doorbell owner is that those pictures are then being shared with 1,300 police forces across the country, who can then use that to set up virtual lineups. So if a crime takes place in your area, you happen to walk past this door, you could end up in a virtual lineup. And we're starting to see cases of that. Robert Williams in Detroit is a great example of that. He was arrested after being put through a virtual lineup. Apparently, he was charged with stealing some jewelry. And then it turned out that he could prove that he was 30 miles away from the crime because of social media. So that's kind of a way that they interflect. But the reason that there was a false identification is in the training of that machine, there were so few Black digital images that just like the robot could not walk in that first example and was falling over, there were so few Black faces in that data set that it literally couldn't recognize. So it ended up matching against just a general Black face. And that really harks back to two things. It harks back to the extremely hurtful and racial joke that all Black people look alike, which we know is not true. We are individuals, we are three-dimensional people. But then it also, from an American perspective, kind of harks back to the founding of this country and this idea that Black people were only 3/5 of a person. And so we're looking at the use of facial recognition in the context of policing because we're worried, and we're seeing cases like Williams's case, Niger Peters in New Jersey, the same story. There was another case in Detroit, and for New York Times readers, there was a huge story in the Times yesterday that was looking at Clearview AI, which is one of the most notorious companies because the way it gets its pictures to train its system is by scraping social media without our permission, and then is being used by the police. And in the Clearview article yesterday, because of laws in Illinois that do not allow for that type of invasion of our privacy, the company were forced to take the pictures in Illinois. But what happens to the rest of us? What happens to you all in Texas? What happens to me in New York? What happens to our brothers and sisters in Michigan and Georgia and all of the other states? And that kind of takes me to the other part of our work. So we build these case studies, we make the case, but then we're always focused towards policy. So on the social media algorithm front, in 2019, I was extremely honored to be part of a team that introduced the Deepfakes Accountability Act. And that's when we were really introducing at the federal level statute that spoke to these algorithmic systems that we're building, artificial intelligence, and the way it's going to revolutionize our economy and revolutionize the way that we shop, the way that we work, the way that we sleep. I mean, imagine 20 years ago thinking about the fact that we could talk to our phone and then our phone could order our food. That seems ridiculous. Here we are. That's a reality. That's been our reality in COVID if you wanted to. I personally wouldn't do that because of privacy concerns, but we can get to those questions later. But within that statute, what we were saying was, number one, we want to know what are the human costs of these technologies, not just the amazing promise, but what happens if you're not just parking a car? What happens if you're not just trying to navigate a robot through terrain? What happens when those predictions are being made to whether you should receive benefits determination, which was something that happened in Michigan, where they were using an AI system to try and catch people that had a history of fraud. The system itself wasn't precise, and then 5,000 people were denied unemployment benefit during COVID. That type of algorithmic decision making at scale really has an adverse impact on the poor. It has an adverse impact on women. It has an adverse impact on Black folks. What if you're Robert Williams and you were arrested because you are Black and the computer cannot recognize you? That's what the Detroit Police Department said to Roberts, and he's now in litigation. What if you are on social media and you truly believe that the vaccine doesn't work because you're being fed these messages that you're already already becoming primed towards, that you already believe to be true, and then you're acting on poor public health information. We really want to make sure that there is some type of catchment system for that, some type of agency like the FDA to decide whether the algorithm is safe, and that there is a maturing of the conversation that pulls back from the technology to itself and then puts forward what this technology is going to do in human life, and how can we work with scientists, with journalists, with artists, with all of us. It's going to take all of us to create systems where we can unleash this incredible power to live in a society that is more just, that is more fair, and that is really one in which all Americans and our brothers and sisters throughout the world can benefit from. So that's a little about me, and I really, really look forward to questions.
Awesome. Mutala, I have a couple of immediate follow-up questions. I want to quickly ask Michael if he got his kinks worked out on his on computer right there. Michael, were you able to get something going?
Yes, I was. I can be less ambitious with showing all the videos at once, and I think it'll work this time.
Okay,
And
let me ask.
Michael, your presentation was amazing, by the way. It's just COVID.
Michael, I'm going to get to you in just one second. I want to start with one quick follow-up question for you, Mutala, which is, you know, all these issues that you're presenting lead me to ask what can be done to improve AI to lessen bias. I mean, really, because even going back to the time when I was 10 years old, 9 years old, programming BASIC on the computer, and you say the computer is only as smart as what you put in it, right? So is it just, does it mean feeding it massive amounts of data, black faces, brown faces, people from all over the world? I mean, it's really the data that goes in is what makes it more. Is that it? What do we do?
Well, it really depends. So in that particular case, Claire Garvey at Georgetown Law issued a report called Garbage In, Garbage Out, which is something that anybody in the technology world, particularly my career, which has been in product design, so not so much on the academic side, but how can we use this science to create this thing so that we can sell it, right? That was my entry point. And then I kind of got into the social impacts. You have to ask a couple of questions. Yes, you could, in a world in which policing did not have a culture of racism, you could put in more faces, it could become more accurate, and then yeah, the system works. The problem is the underlying systems that we're upholding and we're strengthening.
Who built it in the first place?
Who built it in the first place? But also, why are they building it? So what happened in Garbage In, Garbage Out was to make the system more accurate. Lawyers over at Georgetown found that they were drawing the rest of people's faces, because facial recognition is not a facial recognition box. You have an architecture that supports it: CCTV cameras, Ring doorbells, self-checkout. If you use any type of public transport or go into any type of public space, the images that are captured, that doesn't mean that they're good images. Just think about how many times people take selfies. So even the images themselves, even if the technology is perfect, that doesn't mean that the digital input is perfect. Number two, do we have the right to privacy in free space? If I am not committing a crime, but I happen to walk past your door because you have a Ring doorbell, I have the right not to be under suspicion. And one of the great things about the United States is this presumption of innocence until proven guilty. These AI systems, as they become more as they become more powerful, if used in that way, takes away that provision. So that's why I always say this cannot just be a purely technical conversation. Make the system better, it's fine. The third thing is, what are the good applications for this? So we may not want to use facial recognition in policing. We may not even want to use facial recognition in on human subjects. That's a different question. But in the context of policing, if we want to keep up this presumption of innocence, and if we want to make sure that that evidence isn't going to be used as due process for arrest, then we have to think of more life-affirming use cases. And so I was delighted this year when I heard that a group of scientists were using facial recognition to track bears in the wild after wildfires. So they were trying to figure out which species survived, which species didn't, how do we characterize them, and then how do we rebuild this ecosystem to support animal and plant life. And they use this same recognition technology, lots and lots of pictures of bears, right? Then let's recognize the bear. And that was low stakes. If you get the wrong bear, you're not throwing somebody in prison, or you're not, you know, presuming their innocence. So I would encourage people to not to think about the impact that they're having on society, and then thinking about the society you want to live in. And just kind of in closing, these systems at best are used in concert with human decision makers, because we have the ability to change our minds. We have the ability of understanding social context, but we also have the ability we have an ability for empathy and for discernment. And these systems are not supposed to deliver this because they're systems, yet we're expecting them to make decisions where discernment, empathy, compassion, and just human dignity need to be protected. And that's not their job.
Excellent. Thank you, Mitali. Appreciate it. So I want to get to Michael. And also, I want to note for those who are watching this online right now that we do have a chat box that you can ask your questions in right there, and we will get to your questions. We're going to go a few minutes past 1 o'clock today, just because we started a few minutes after noon. And so I want to make sure that we get your questions in as well. So you'll have time to ask of any three of our presenters a question. Okay, Michael, take it away and continue. This is like where we left off, so to speak.
Yes, yeah. So thanks, Mutale, for picking up the slack and actually providing some good segue material as well. So we left off at computer vision. The next extension of machine learning that has been going on in my division is into medical diagnostics and prognostics. The origination here in the industry was a breast path Q challenge, which was international challenge with over 100 entries, where SWRI came in first in detecting breast cancer cells in digital pathology images. So kind of drawing from that computer vision expertise and applying it to healthcare. And additionally, in collaboration with UTSA and UT Health, SWRI has developed one of 4 models currently used by the city of San Antonio to forecast COVID-19 spread across various levels of mobility. So that's work that's kind of happening around me, but my direct involvements are mostly in energy and environment, as well as human health and traffic management. So there's no videos this time, but the first technology I wanted to highlight was is hydrocarbon leak detection technology that we have a patent for. We call it Sled, Smart Leak Detection, and it's used both for liquid and gas hydrocarbons. So we've developed Sled M, which detects methane autonomously from an aerial platform, a drone, as well as crude oil detection on multiple surfaces, including various types of terrain and also water. The videos would be cool, but I'm not going to risk it. I'm also heavily involved in Searchlight, which is a machine learning driven decision support system for non-targeted analysis of chemical samples. So that's a lot to unpack. Non-targeted analysis is a suspect screening methodology on chemical data to find compounds of interest in chemical samples. So an example of this is finding 4 times more ingredients in a consumer product, like a lipstick or a shampoo, than are listed on the ingredients on the label. So Searchlight sort of empowers the analytical chemist by identifying the patterns between chemical samples and freeing up their time to do the more grueling work of interpreting those patterns and providing insights into what the chemical structures and characterization of the samples means. So this is an example of keeping a human in the loop to provide decision making and really just processing the data and allowing them to use their human powers, if you will, their expertise to provide insights on what the data means. The last project I'll highlight is liver transplant decision support system that we've developed recently to predict 90-day mortality in liver transplant recipients. So this is developed over a public data set of national liver transplants, and we have surpassed the state of the art in both machine learning models and the clinical measures that are currently used in practice. But probably more importantly, this research has centered on providing explainability metrics for the model itself. So we typically call neural networks a black box model, which means that it doesn't provide, it's not easy to understand how it's making a prediction. So in order to sort of work around that, we employed a method for quantifying the feature importance, the variables going into the network that are providing the most information for a specific patient. So I gave an example list for one patient of the top 15 predictive features. And the main point of this is to provide a clinician support for making their own decisions. It's not to make a decision of who deserves a liver and who doesn't. It's more just empowering the human to make a more informed decision. And that kind of leads into my research interests, my personal research interests, I should say, which is decision making, both from a computational and a human perspective. I'm also interested in human level AI, or strong AI, as we call it in the field, which is a little different than the narrow AI examples that I've given, where machine learning is used to perform a specific task. But I try to draw elements and be inspired by human processes in my day-to-day work, and draw from that to create innovative solutions to very specific problems. And I also think that it's imperative for responsible development and use of machine learning systems to have an interest in bias. Both from a cognitive and modeling point of view and from a data bias point of view. And Mutale did an excellent job highlighting the dangers of getting these, or maybe not appreciating the issues here. So there's two sides of this bias problem. I think data bias has been discussed quite a bit already. Sort of underrepresentation within a data set of a specific group or class. And it can also come from sort of the historical prejudice built into a data set, kind of the human or institutional process that creates outcomes. The other side is the mathematical definition of bias, which parallels very closely to cognitive bias. So that's sort of the difference between an internal or subjective understanding of reality versus the objective or collective reality. So the mathematical definition kind of fits there, and it's similar in a model. But I think both of those contribute to errors, and we've seen the danger of making those errors already. So it's important to appreciate them and take care as we develop these systems in the future. And thanks. I look forward to answering questions.
Thanks, Michael. Thank you very much for that. We appreciate it. So we're going to take about 10 minutes here and go over the top of the hour for your questions. And if all three presenters could go ahead and turn on their camera. The first question comes out to all presenters. And Elizabeth asks something related to AI and intellectual property. That is, should AI systems be inventors or authors? Should AI algorithms be patented?
Many are. That's certainly in my work, how we can figure out what Apple wants to do or what Amazon wants to do. A famous example of in New York City, where I live, when Amazon was supposed to be coming to New York, one of the tools that organizers used was going into public records to find that there had been a new robot for classifying, I guess, a warehouse robot that had been patented that if used would have had all of these implications on labor. So kind of going back to what Michael was saying in terms of institutionally, the robot itself isn't the issue, the AI itself isn't the issue, the computer scientist isn't the issue. But if you use a robot that then has these labor implications, the system itself. So that's definitely something that I've seen. And then when I was working in Congress and we were, you know, hearings were coming up, one of the things that my team would do was look into patent records to see what they're doing, but they're owned by the company and it's often under different names. So it might not be Apple, there might be a different name and you just have to figure out who it is.
Michael or Dorisha?
Yeah, I think AI systems or AI hardware has been patented for a while now. I think beyond what Mutale is saying, I'm coming in from an engineering perspective. I think these systems can accelerate a lot of our problem-solving capabilities. So I think there's a report from Computer Research Association which calls these as problem-solving amplifiers. So in a way, they're able to solve some real world engineering problems like Michael has pointed out, and even Mutale has pointed out. There are other complexities with where the technology is today. And I think these can be addressed as we are going along. And some of those things are going to be how we are thinking about integrating these systems together and what additional problem sets they are being used in real world, how are they being deployed in the real world. And a lot of times engineers do not have this context or at least that broader understanding. And exactly to this point that Mutale has brought up earlier, it is very important for us engineers and scientists to work with a broad discipline of people as these solutions are being deployed in the real world. Whether this is AI ethics researchers or whether this is researchers who are thinking about the implications of deploying this in the real world, the community as well. And that is what we are trying to do in our consortium. And I think there are several others that are being built up in that same ethos, as in we should try to bring people together to solve these problems rather than trying a computer scientist building an algorithm and or patenting it as a system and not completely being aware of the consequences of such a deployment.
I would agree completely with that sentiment. I think it's a problem in data, right, where we don't have representation or diversity. It's an equal problem in the research team as well. We need different perspectives to cover the blind spots that any one individual might have in terms of developing a holistic system that's responsible and helpful for humanity.
And just a quick note on teams, we also have to know how to talk to each other. So I used to always laugh that when I would work with engineers, you know, policymakers and law people, we say no, we don't want to do anything, whereas engineers want to do everything. They want to create, and so even having that even understanding and getting away. I'm so glad that this idea of the individual engineer being the problem, that isn't the case. If these engineers are working, the only example I can give you is Google, but if you work for Google and you're told to make a product, you're just told the specs of the product, what the budget is and what the time is. You might not even know how that's going to be deployed. And that's why you see so much friction at Google when around Project Dragonfly, where the engineers themselves said, no, we don't want to build the search engine for China. We just want to be engineers. So also remembering that, I think, is really important.
Adam asks, Mutale, is there any open repository or portal with lists and or examples of bias to help AI, machine learning, or analysts vet their proposals or even vet present projects?
So there is a body of work growing. My work is really loosely termed as ethical AI, and until God, I'm saying Google so much in this. I really don't mean, hi Google. I mean, don't get mad at me. You can't get mad at me, whatever. But Google was actually one of the leading places that had a really robust AI research area. The issue with academia comes down to NSF funding. Sorry, now the NSF are going to be mad at me, that they really don't invest in people doing this work, whether it's in the university setting or in the research setting, at the same levels that companies invest. And the difference between having somebody at university, or I would hope at a nonprofit, doing this is that there is this idea that it's for the public good. When so much of this research is in-house to give us, I don't know, a faster way to buy boots, I don't know, whatever. That's not necessarily in the public interest, and they're the ones developing the research. But just to give you a few starters, definitely read Cathy O'Neill, Weapons of Math Destruction. She had a PhD from math, then became a data scientist. Definitely read Algorithms of Oppression by Sophia Noble. Definitely read Automated Inequality by, and I can definitely email through a robust reading list and articles. These articles are showing up so much in the academic press across every single discipline, both in engineering and outside, which is why the Matrix consortium to me is so exciting.
Mutale, anything you email to me, also I'll put up in the follow-up post online when we post this video on our website later on. Kimberly has a question we'll get to in just one second. Michael, I have a quick follow-up question that stems from the very beginning of your presentation when you were talking about traffic patterns and the way AI uses and for autonomous vehicles. And this is maybe sound like a really dumb question, but it's my question, and I specialize in dumb questions. So how does AI prevent autonomous vehicles from having a Wiley Coyote moment? And what I mean by that is where, they're driving down the road, and if somebody were to paint the road on the side of a building somewhere to mimic the road in front of them, why doesn't the vehicle gonna crash into that that wall right there?
That's not a dumb question at all. That's a very good question. One of the projects that I didn't highlight here, but I was considering it, is called adversarial examples for machine learning, specifically deep learning, which kind of takes advantage of that black box because we don't have transparency into the decision making. There's actually ways to kind of hack the very specific way that information has been encoded into the model. So it's not even as difficult as painting a road. There's actually like noise patterns that are it's not very sophisticated, but you can take advantage of how information is being represented and passed through a neural network and trick the system in very surprising ways. So, kind of missing the object classification, forcing an autonomous vehicle to perhaps see a tree as a person or vice versa, or a car as a building or as nothing. These are all serious problems that need to be addressed, and it's an active field of research.
Yes, adding to that, to Michael's point, actually, there is something called continual learning, that AI systems need to be able to learn continuously through their lifetime as these new inputs are coming in. And as I was pointing out earlier, brains can do this. I mean, we can argue about that, perhaps, if we learn continuously through our lifetime. But brains have these features. So why are AI systems not able to do that? And that's an active research that we are currently doing with DARPA called lifelong learning. And this is a classic example that you pointed out, Nathan, about the autonomous vehicles. What happens? How do they react when these new unexpected inputs or objects are seen in their viewpoint? You do not want them to catastrophically fail. That could have serious consequences. And you want these algorithms to, even if it's a new input, probably somehow gracefully degrade in performance or kind of make the right choices. So this is a very active field called lifelong learning or continual learning. So hopefully in the next, we might have solutions.
Let's see here. Last question from Kimberly is, this may be for you, Mutale, at first, which is, have we as humans given up any right to personal privacy, our face, our activity, our habits, just by simply existing and interacting in society now?
Yes. Sorry, I'm known as a professional Debbie Downer, but if you walk outside, your picture is going to be taken. I talked about social media being a place where our faces, we don't only just share our faces for identification, but then we keep taking pictures of our faces as they age and they change to make these systems better. And then that information could be used against yourself. And this is one of the reasons why I'm always really interested in not just the research that's happening in the engineering world, but then thinking about what legal frameworks do we need to react to this, because it seems to, at least from my vantage point, got to a place where the expectation of privacy isn't even something that we consider, yet we're always constantly complaining, I don't have any privacy. And one of the areas I see that so much is in this idea of cancel culture, where people can go back and see what you did 20 years ago and then decide you're a terrible person now and decide that you haven't changed. And sometimes, let's be clear, sometimes these are really, truly terrible people, but sometimes they just did something wrong and they did it 10 years ago, but because they did it in the public domain, we now have that institutional memory. Now imagine if we then program that into our machines and we start saying things like, and this is a New York City example, this was a proposal under Trump, if you had ever had public assistance and then you went for naturalization, it would be denied because you are on the public charge. That's not fair. You may have had public assistance for a number of many reasons. It could have been that you were in COVID and you lost your job and you needed some unemployment, and then you find a job and you're productive and then you're going through this other system, but that data stays. And then that data could keep you out the country. So yes, we've lost privacy, and luckily, yes, we can get it back. And I'm a crazy optimist because there's many steps, between that, but it's something that we can certainly think about, and it's something that we can remedy, and something that we should hold. It's precious.
Well, we're 13 minutes past 1 o'clock, and so we're over time. So you've been very generous with your time this afternoon. I feel like I could continue talking to you and listening to you, especially for another couple of hours this afternoon. But I want to thank our participants today, Dirisha Kurisapudi from UTSA, Michael Hartnett from Southwest Research Institute, and Mutale Nkonde from AI for the People. Thank you all very much for sharing your knowledge this afternoon today.
Thank you.
And we want to thank We want to thank CodeUp, Mind Science, and UTSA Knowledge Enterprise for their support of Think Science today. This presentation, as I said, will be on our website next week with additional links that anybody provides to me. Presenters, Darisha and Michael, if you want to send your slides along, I can put them up as a slide share on there as well. And we'll be able to share it with a friend next week as well so that they can learn from this as well. And our next Think Science discussion online again will be coming up in May. So I hope you'll participate in that, those of you who are watching. I'm Nathan Cohn, so stay safe, keep wearing your masks, and we'll see you soon, okay?